Hello, everybody. We are starting a new chapter on buckling, the concept of buckling. So this is going to be a quick chapter. We're not going to be covering that much. Just a quick derivation of where the equation for P critical, where does the formula come from, and then basically just a few examples in a couple of more videos. So let's get started and let's talk about buckling. So let's say if you have a bar under a compressive load like P here. So we know that we have to watch out for like the normal stress sigma, which is just simply P over A. Obviously, it must be less than yield or ultimate stress, usually yield. So you don't want to get into the plastic zone. So that's one thing to watch out for. Also, this guy could deform. So maybe you had set some allowable deformation. So you want to make sure that the deformation that is generated by this compressive load is what is less than whatever you have set in your in your design. Now, one thing that we sometimes overlook in design is that what if this load caused buckling? By the way, obviously it is clear, it goes without saying that if a member is in tension, right? If a bar is in tension, no buckling obviously is going to happen. The member has to be what? Clearly in compression for that to happen. All right, so what if it buckled before it yielded or before you had the deformation that you had set? So we got to make sure that the load that is acting compressively in the bar is less than what we call a critical load. Okay? So P sub CR is called critical load, and this is the load or the smallest load which cause the bar to buckle. All right, so how do we determine this bar? You will see in a few minutes that this load obviously has to do with the length of the bar. It has to do with the material that is made of. So L, the material, modulus of elasticity, and also moment of inertia. So these are the three parameters that will determine what that critical load is. Okay, let me just erase this and get started on the derivation. So let's consider a bar that is pin connected. Right? By pin connected, I mean kind of like a roller connection at A and B. So the ends are what? The ends are free to buckle due to this compressive load that we have applied at both ends, right? So what's important is that the deflection is 0 at A and deflection is 0 at B. So that's what I mean by pin connected, but it's allowed to buckle. All right, so what we want to do is to start by cutting the beam, right, at a certain section at a distance x, and then show the internal forces due to this compressive load that is applied. So clearly there would be a normal force. There is not going to be a shear load. So the shear load is going to be 0 because we don't have any load in the y direction. And then there is an internal moment that we have to determine. So taking this guy as x and this height as y, as shown here. So we say, okay, taking moment about O where we cut, m plus the moment of this p about here is p times y. So be careful, x is not going to be here in this equation. Okay, so m becomes minus py here. And then we go to the differential equation of the elastic curve. EIY double prime equal m. So EIY double prime equal minus to py, right? And then bring minus py to this side. So it becomes EIY double prime plus py equals 0. Notice that before, our moment was always a function of x, guys. Remember when we were doing deflections by integration? So moment was always a function of x because we had loads in the vertical directions. And then simply we integrated once, we got the equation of the slope. We integrated twice, we got the equation of the deflection. But that's not the case here. We have to solve this equation now. Okay, so let's move to the next page. So what is the solution to this equation? EIY double prime plus PY equals 0. So the first thing I'm going to do is what we call normalizing the equation. So we divide by the coefficient of the highest derivative, right? So EI gets cancelled, so we get Y double prime plus P over EI times Y equals 0. Now, for convenience, I'm going to set P over EI equal to omega squared. Now you might wonder why omega squared? Why did I pick omega squared? Because actually the differential equation that you see here is the same exactly as the differential equation of a mass connected to a spring like this, and say it's given the displacement of y. And omega is the natural frequency of this system, which is actually the stiffness divided by the mass, the square root of a stiffness divided by mass. That's called natural frequency. And in a way, this differential equation mimics this differential equation of this guy, which would be my double prime plus ky equals 0. And then y double prime plus k over my equals 0. You see how I call this, see, this is your omega squared. So that's the reason we are doing this. Anyways, back to here, if you set that equal to omega squared, now this is much easier to handle. Y double prime plus omega squared y equals 0. Now, we have to assume a solution of the form. So you ask yourself, what would be the solution to something that you take the second derivative of that something and then you add in a way to itself, of course multiplied by something else? You get 0. Must be what, some exponential function or sine cosine, because the derivative of exponent is kind of repeat itself. Sine becomes cosine, the second derivative becomes again sine, and so on. So we assume an exponential solution of the form y equal a e to the lambda x. And the way, after you make an assumption for the solution, you have to plug that back into the equation. So we need y double prime. So we take the first derivative and the second derivative becomes a lambda squared e to the lambda x. Now we're going to take this guy and plug it in here. And this guy would go right here in place of y. And that's exactly what I did here, guys. Now, I factor a e to the lambda x because that's common. I end up getting lambda squared plus omega squared. So I have two possibilities now, Either a e to the lambda x must be equal to 0, and that's not good, because if you say a e to the lambda x equals 0, basically you're saying your solution is equal to 0, which would be what we call trivial solution. Therefore, this guy must be equal to 0. If we do that, we end up getting two roots that are complex, plus and minus I omega. So we have two roots, lambda 1 and lambda 2, one with positive, one with negative. Which means now the solution is going to be a combination of the two roots. Some constant a1 and some constant a2 involved. So let's go ahead and put lambda 1 and lambda 2 here. I omega x, right? Because this is lambda 1. This is lambda 1 and this is lambda 2, right? Now, where do we go from here? We don't want to leave the solution like that. That's not convenient. That's not going to get us anywhere. So we use Euler equation. Now you know one of the famous Euler equation is e to the I theta plus or minus becomes cosine theta plus or minus I sine theta. If I plug that in place of this guy and this guy, so I'll put them here and here, and then factor cosine omega x and sine omega x, we end up getting a1 plus a2. Cosine omega x and then plus a1 minus ia2 sine omega x. Now, right now, let me go to the next page. a1 and a2 actually are complex constant. That's why we don't want to deal with a1 and a2 lowercase. But a1 plus a2 becomes real constant, and I can show this to you quickly. See, what happens that is a1 and a2 actually are, if you determine them by boundary condition, they are complex conjugates. So for example, if a1 is, say, 2 plus I3, and a2 is 2 minus I3, because they're complex conjugates, what happens to a1 plus a2? Look at that. a1 plus a2, I called it uppercase a1, right? Here. If you add A1 to A2, you see these two cancel, and A1 to A2 becomes A1 equal 4. This is just an example with numbers. Similarly, if you try this, also it becomes a real constant. Okay, so that was the idea of using the Euler equation. So forget about the lowercase a1 and a2. Now we are dealing with uppercase a1 and a2. So now our equation becomes a1 cosine omega x plus a2 sine omega x. Okay? All right, so how do we find a1 and a2? We use boundary conditions. What are the obvious boundary conditions? At x equals 0, deflection is 0. And at x equal L, again, deflection is 0 because they are confined, right? When you put it under this axial compressive load, right? All right, so when you said x equals 0 and y equals 0 here, so y is 0. When x is 0, this becomes 1. Cosine 0 is 1. And this becomes 0. Cosine 0 is 0. So a1 must be equal to 0. So that means that actually our solution is going to be a sine wave, since a1 is 0. Now, the next thing is boundary condition is this guy at x equal L, y equal 0. So if you do that, you get 0. Remember, a1 is already gone, so we get a2 sine, in place of x put L, sine omega L. Again, we have two options. Either we have to say a2 equals 0 or this guy equals 0. If we say a2 equals 0, then we don't have anything. A1 was already 0 and now a2 is 0. That's no good. All right, so we say sine omega L equals 0. Sine of what angle is 0 besides 0? Sine 0 is 0. Has to be a multiple of pi. So I called it n pi. N could be 1. So we know sine of 180 is 0. Sine of 360 again is 0 and so on. All right. So remember now, omega squared was what? P over EI. Remember we did that we used that substitution for convenience. Now it's time to actually put it back. So what I did, in order to bring omega squared, I squared both sides of this guy. Right? So I got omega squared L squared equal n squared pi squared. Now what is omega squared? Is P over EI. L squared equal n squared pi squared. So I said, okay, let's find the smallest load. Let's set n equal 1. The smallest load would be then pi squared EI over L squared. That's the critical load. That's the smallest critical load needed to buckle this. Of course, this is for this particular case, guys. Remember that. Pinned or roller, whatever you want to call it. Just a reminder that actually P critical, if you don't set n equal to 1, is n squared EI pi squared or pi squared EI n squared divided by L squared. So I set n equal 1 and I ended up getting this. So this is the smallest critical load that we could have. Let's wrap this up, guys, and then look for some videos with examples. Okay, so the smallest critical load for n equal 1 is this guy. That's called actually the first mode shape. So how would this guy buckle due to these compressive loads? It would buckle like that. That's for n equal 1. All right, what if we set n equal 2? Look what happens if n is 2. Remember, it was, what was the critical load? It was n squared EI pi squared, right, over L squared, right? So when n is 2, this becomes 4. So what does that mean? That's first of all called second mode shapes, right? So now, that would never happen unless if you do a confinement. If you confine the middle of this bar, let's say of length L, right? So this guy cannot, has zero deflection here at this location. Then you apply a load, you reach this first load, and nothing happens because it can't be like that. But then when that load becomes 4 times of this load, it will go to its second mode shape, and this would happen to it. You see that? And then similarly, the same story. If n equals 3, that load would be 9 times. But you have to have some kind of confinement. So you have to have a confinement here and a confinement here. So this guy cannot, this or this cannot happen. But once the load reaches 9 times the smallest critical load, you would see this would happen. And this is called the third mode shape, or it's for n equal 3. Hopefully I haven't confused you guys. This is a very really simple concept. We basically concentrate on the smallest load that causes buckling. So I'm coming shortly with some examples. As always, thank you for watching and listening.